Greetings. One of the things that comes along is with Egyptian arithmetic is their ideas. And the Egyptians have some really bizarre ideas about how to do things. And they don't understand pi very well. They've got a really messed up formula for the area of quadrilaterals. But one thing they do have, and you might think for some strange reason, they know how to find the volume of a pyramid. That's rather important to them. Why? They're building them all over the doggone case. So if you're going to build them all over the place, you need to know how many rocks you're going to need to use to make them. You better have a good formula. And for the Egyptians, they actually had the correct formula for the volume of a pyramid. They knew, hey, give me a base, give me the height of the pyramid, and from this, I can give you the volume. And the volume is 1/3 the area of the base times the height of the pyramid. And this is marvelous. And with this, the Egyptians were able to do a lot of fantastic calculations. Now, let's suppose that we are building a pyramid. One of the things we need to know is not just the volume, but I need to know the volume of something else. I need to know the volume of the pyramid when I get it built. But the problem is some of these pyramids are taking us 20 and 30 years to build, according to the most recent archaeological data. You don't just throw one of these up next to nothing tomorrow. So we're building this, but somewhere along the line, you get this. And let me show you what that is, because you're looking at too much of it. And there it is, a truncated pyramid, meaning it's not finished. I've built part of my pyramid. I'm trying to build this pyramid, but this is where I've gotten to this year. And so the question is, next year when I come along, I need to tell the stone quarry masons how many stones to cut. Well, if I'm going to keep doing this, I better know what's the volume of the missing piece. Also, I really want to be able to tell my boss I did a lot of work this year. I need to know the volume of this piece. And this is what the Egyptians also knew how to do. So let's take a look at one more drawing, and then we're going to take a look at how we know it works so well. So imagine we have a pyramid that we're wishing to build. And we know we've gotten to some height along the way, and we're still going up. So what I need to know is a couple of facts about this pyramid. I need to know, one, this measurement right here. What is the height of this monstrosity when I get done? The second thing that I need to know is right now, what's the height of what I've built already? And how are those two things going to be related? And the Egyptians said, not only can we do that, but we can tell you exactly how this is all going to work out because we know the volume of the bit we've already built. That being the case, let's take a look at that formula, but I'm not going to give it to you for free. We got to figure it out. So we know the volume of a pyramid is 1/3 the area of the base. Most of the bases that we have are squares. So it's side squared times h for height. Good. We're in good shape. So let's take a look at this triangle right here, or this pyramid. And what I'm going to do is I'm going to look at the central triangle if I slice it through the middle. And if I slice it through the middle, it's something looking like this. And we know we've built up to this point, and we're building all the way to here. Now, to make my calculation somewhat easy, I'm going to let the base of the pyramid be represented by B, the top plateau by A. And we're going to pick a couple of variables to represent various amounts of information I have. We've built up to a height h. We have x more to build. And the question is, how is this going to work out? Well, I could just as easily have cut this in half, making nice, neat right triangles, and have half of B and half of A, and tell you, hey, I've got similar triangles. It's just as easy for me to have them out here, and I can tell you the following. I know that B is to the total height, x plus h, as A must be to x. And what we want to do is I want to see if I can get rid of one of these variables. And you'll see why in a moment. So what I'm going to do is I'm going to multiply the extremes and the means. And I get bx is equal to ax plus ah. So I have bx minus ax is equal to ah. I'm going to factor out an x over here, and I have b minus a is equal to a times h. So x is going to be equal to a times h over the difference of the two bases. You're asking yourself why. I would rather have 3 variables than 4 whenever possible. So now the calculation shouldn't be too bad. The volume of a pyramid is 1/3 the base, in this case b squared, times the height h plus x, and then I'm going to subtract off the pyramid that I don't want since I'm looking for a truncated pyramid. So that's 1/3 a squared times x. But we now know what x is in terms of these other letters. So let us put that in the formula. So the volume is going to be 1/3 b squared h plus x, which is a times h over b minus a, minus 1/3 a squared on 2 ah over the difference of b and a. Now this is nice, and you may not think about it yet, but I think we're going to see something pretty come out of this. So the volume of a truncated pyramid is going to be 1/3, and what I'm going to do before I distribute the b squared, I'm going to get a common denominator in this piece right here. So I'm going to have b minus a. So this means I have h times b minus a plus a times h minus 1/3, and over here I'm going to have a cubed h over b minus a. And the so you now see getting the common denominator made sense because both terms are now going to have a denominator of b minus a. So I'm going to have volume is equal to, and I'm going to collect all of my denominators together at one time because I have common denominators to both. I have 3 times the difference of the bases, and I'm now going to have b squared times h times b minus h times a plus a times h minus a cubed on h. Now, this is going to be nice right here because notice h onto a is the same as a onto h, so these two bits are going to subtract out, leaving me simply b on h. And I already have a b squared, so I'm going to get a b cubed on h. So the volume of the truncated pyramid is going to be b cubed on h minus a cubed on h over 3 times the difference in the measurements of the bases. I'm going to pull that h out for a minute because I think it's in the way. So I'm going to have b cubed minus a cubed all times h over 3 times the difference in the bases. Now notice, if we remember our college algebra, which I certainly hope we do, b cubed minus a cubed is one of those known forms for factoring. So all of a sudden, I'm going to get b minus a, b squared plus b times a plus a squared, don't forget the h, all over 3 times the difference of the bases. But notice b minus a and b minus a will take care of themselves by division, and I'm left with a very simple formula for the volume of a truncated pyramid. And it is b squared plus ab plus a squared all over 3 times the height. And that h is the height to wherever you've built to so far. And there it is. And the thing that's of beauty is, hey, I don't know about you, but every time I ever factored a cube, I always wondered, was there any practical bit to this piece right here? Was there something we could do with it in some type of manner? And lo and behold, I needed to get a truncated pyramid volume. And the Egyptians had this formula. Why did the Egyptians have this formula? Because they were building pyramids. Practical knowledge. They would have never gone through all of these steps. I bet you they built their formula by trial and error more than anything else. That's my supposition. The Greeks were practical, not theoretical mathematicians. I hope this helps.